Now we have said that the US uses DOP, the British use sodium chloride, the Germans use paraffin oil, the French use a urine dye. What do the Russians do? What did the Russians use? The Russians used common sense. All of you are familiar with the story that the American astronauts were complaining that the so-called clean room pens that were given to them, the ink flow was erratic out in zero gravity in outer space. So NASA set up an expert working group that worked on this problem, and they came up with a pen that was space qualified. They spent $150 million on the project. But the Russians, for the 4 decades or 5 decades that they've been in space, never bothered. They used common sense. They used lead pencils. Now, the Russians have not used photometers, have not used aerosols, have not used particle counters. So what did they use? They used their eyes and a microscope. Now let me tell you their technique. They use a normal filter holder with a 0.47 micron filter paper. They connect it to a volumetric pump and they draw the known quantity of air. Whether they are checking a filter or whether they are checking the room or environment, they use the same technique. They expose the filter to a certain known volume of air, take it to the lab. There is a control filter paper and there is the test filter paper. They use an optical microscope, a comparator microscope, to find out what are the particles and how many are there. Simple. Now, why did the Russians opt for optical microscopy? Simple. Human hair is 100 microns. The eye can see it. The naked eye, unaided eye can go down to about 50 microns. So all that they argued was, if you provide an aid by way of a microscope whose magnification is 100 or 200 or 400, even with just 100, if you can see 50 microns with unaided eye, with a magnification of 100, you can see 0.5 microns. So why do you need anything else? That was their logic. Now, it is not as if the Americans or anybody else were not aware that you could use microscopy. In fact, it has been mentioned as a method in US Field Standard 209E way back in 1992. US Field Standard 209E, Annexure A, gives you a full detailed SOP. US Field Standard 209, Annexure A, counting and sizing of airborne particles using optical microscopy. And what is more interesting is even ISO 14644 Part 3, in its Annexure B3, in its para B3.3.2.1, speaks about filter collection and microscopic measurement of microparticles. That's the catch, macroparticles. Now you see, 14644-1 said to the buyer and vendor as agreed between them as to what is the interval in which they are willing to work. What is the cutoff particle size at the lower end and what is the cutoff particle size at the upper end. And they only said the upper particle size cutoff should be at least 1.5 times the size of the lower, smaller particle size. But what is the interval is left to you. In the pharmaceutical industry, the regulators have decided for us what is the lower cutoff and what is the upper cutoff. Lower being 0.5 microns, upper being 5 microns. In electronics, lower could be 0.1 micron and upper could be 1 micron. So anything below the cutoff is called an ultrafine, and anything above the cutoff, higher particle size cutoff, is called a macro particle. So in both US Field Standard 209E as well as in the ISO 14604 Part 3, they refer to optical microscopy as an acceptable method for measurement of or counting of macro particles. So if a manufacturer had chosen 0.2 micron as the lower limit and say 1 micron as the upper limit, then 2 microns, 3 microns, 4 microns, 5 microns all form macroparticles. In our case, anything above 5 micron is a macroparticle. But if you can see reliably down to 0.5 microns using a magnification of 100 on any optical microscope, there is no logic in restricting this practice only to particles larger than 5 microns. And the Russians have done just that. Now, what are the concerns about optical microscopy? One is that it is heavily human based, and the reproducibility, repeatability, consistency, even from the same analyst, could be questionable. Whereas if you were to have a particle counter, you expect that the reproducibility, repeatability would be much higher. Now, the other reason could be because it is not just any analyst who can do this, it's a specialist who has to do this. So he will command a certain salary, and the ongoing expenses could become very high. The general approach in the Western world is, if a job can be done by a machine, then better you have the machine than the man. But in a place like India, where automation is prohibitively expensive and labor is relatively inexpensive, for us, the optical microscopy, it would be the way forward, the logical way forward. They use one more technique. They take, for example, for biological sampling, they take a flask with saline. They put a tube through a bung that goes 1 inch above the bottom surface of the flask. They take another tube from the bung which is above the saline level, connect it to a volumetric pump, and gently bubble the air through the saline. The volume of air sampled is known. Now they take this exposed saline to the lab, stir it, take an aliquot and incubate it with growth promotion medium added. And they know exactly what is the bio profile of their environment. Now, actually the idea of gently bubbling through saline solution makes a lot of sense. First and foremost, now if you take the RCA, you cannot relate the air volume sampled to the count that is generated. Then it makes no sense. Here you know the volume of air you have sampled, and you know what is the count that you have been able to recover. There are other advantages. Now if you take an Anderson sieve sampler or the RCA sampler, as the air passes through and the microorganism passes through, it faces a lot of shear forces. In the case of the Anderson, the sieves on the drums, and in the case of the RCA, the fan. Now assuming one cluster is coming as one colony forming unit, and the fan hits it and it scatters and it lands up in 4 different places on the strip, and you incubate it. Instead of one colony forming unit, you see 4 colony forming units. Now assuming one colony forming unit is coming in and either the sieve or the fan hits it so hard that it completely damages that particular colony, you have no recovery. So you had one colony forming unit coming in, but you have no recovery. Similarly, in the filtration, there is tremendous loss because of drying that takes place. So the recovery is not always reproducible or not reflective of the actual number of colonies that originally were trapped. All this is solved when you use the saline flask. They do more interesting things. They ask a simple question, that if there is a particle which is suspended in air and it remains airborne and goes to the return air riser and out of the room, it doesn't give me too much information by counting how many such particles are there which remain airborne till the end. But what does frighten them is a particle that was airborne but ceases to be airborne and sediments out. If it falls out at any point, it could have also fallen onto the product. So what they do is take Petri dish plates which are thoroughly washed. One set is kept as control, unexposed plates in the lab, and the others are all individually identified and exposed in the room during a shift. And then each of them is covered and taken to the lab and examined under a microscope, and they know exactly how many particles have fallen into each plate over the exposure time. They now have a very clear idea as to which parts of the room are getting more contaminated, where there is greater fallout, and which parts of the room are having a low level of fallout. They repeat this exercise for 100 successive days so that any inference that they can draw is valid with at least 95% confidence. Now that they know where there is heavy particle accumulation or fallout, they examine now why is it happening there and not somewhere else. So now they can do an investigation. And having done that and identified the cause, they can do something about the root cause. But at the end of it all, they are in a position to move their critical work away to those areas which are having the lowest fallout, which are the safest from the contamination risk, and move non-risky activities to areas where there is greater aerial fallout, what is called sedimentation profile in the room. In fact, if you see, even this procedure of recovery from fallout from the air, profiling the fallout, is explained in detail in IEST's RPCC 006.2 in its para 6.8. The particle fallout count is explained in great detail. It is called the sedimentation rate test. So it's not that the Americans are not aware of all these procedures, it's just that in the electronic industry it is done there, but in the pharmaceutical industry it's not done. It's not even known. By the same token, if there is a microorganism in the air and it remains in the air and goes out through the return air, it is not likely to ever put the product at risk. But if there is another microorganism which is in the air and then falls out, if it has fallen out here, it could have fallen onto the product. Therefore, they repeat the same exercise with Petri dishes, but this time with saline. Not media, but saline. And they place it around the room, expose it for a known period, cover it, take it to the lab. They have the control plates, they have these test plates, and they use the technique of adding growth promotion medium to the test plates and incubating each of them individually. Now they have data as to where is the greater biofallout and where is the area which is relatively bioclean. They are now able to investigate why was there so much, why is there consistently so much of higher fall out in one area as compared to another area, investigate, find the root cause and address it. And finally, move all the work to those areas which are bio-safe relatively in the room as compared to those areas which are bio-risky or biohazardous. This way, they have not only profiled their facility, monitored their facility, certified their facility, but used all that data and converted the data into meaningful information and applied that meaningful information into knowledge and experience for a better product, better process. No wonder the head of ISRO had once lamented to his folks that though there is so much money spent in our facilities for the so-called clean rooms, they compare poorly with the relatively inexpensive clean rooms he has seen in Russia, where the outcomes are far more consistently favorable. Earlier in my presentation, I had cautioned you that when you are preparing for such an important thing like certification or requalification or even routine monitoring, the presence of a subject matter expert is very, very important. Let me give you some examples as to how the qualifying agency can sometimes mislead you if you don't know the subject. Assuming the qualifying agency is a manufacturer of filters, and if there is a pile-up of filters at his godown, now naturally he is very anxious to offload those filters. So when he does his scanning, he is likely to report as many filters as due for replacement as is possible. So here he says, oh my God, oh no, you're so lucky you called me today, you could have been in serious trouble. I've come at just the nick of time and I think this should be replaced immediately. And he will try to replace as many filters as possible. And you really believe that those filters are due for replacement, even if they are not. Now, assuming that same qualifying agency has no filter for sale in his godown, his media has not arrived, he's run out of media, he's got a pile-up of orders which he's still not able to execute, and now he comes here and actually sees a defective filter. Now what does he do? Now if he says this filter is very defective, oh my God, what is this? You might say, okay, can you replace that filter? And he says, sorry, I don't have the filter. So you'll go and buy it from his competitor. So he doesn't want that. So what does he say? He says, there seems to be something brewing here. It's not serious yet, but it could be. Now I'll do something temporary and I'll fix it for you, and you can use it for the next 5 or 6 months. And he does some repair. And he checks all the filters, and wherever possible he sort of does at-site repairs and says, listen, I think you better indent now, and in any case it will take you 3 to 4 months before the filters arrive here. And so the next time when I come, I think I will replace these filters. That's what he's going to say. So if there is a leaking filter and he doesn't have a filter, he will not warn you about replacement due. And if he has too many filters and he is anxious to offload them, he'll try to offload them on you at the slightest pretext. Lastly, one more thing that actually happened is that an agency went across to test filters at a facility, and the reading was consistently 18, 20, 18, 20, etc. So the person who was accompanying him was a very knowledgeable person on clean room design. So he just requested that agency to bring the apparatus outside the clean room into the open field outside and asked him to take the measurement. And the measurement there continued to say 17, 18, 20. Now very many times you may not be aware that if I am the person who has designed the facility and set up the facility, and I am there to come and qualify my own facility in your presence, failure is not an option for me. So I will do whatever it takes to adjust and manipulate my particle counter in such a way that it gives you good looking readings, attractive readings, acceptable readings, and never ever show something that might compromise my reputation or even the balance payment that may be in your hands awaiting release on condition that the testing is successful. So the pump speed can be adjusted, There are ever so many things that can be done. There have been cases where when the user is watching the probe, the technician is stamping the sampling tube so that air drawn in is reduced. Therefore, particle count is reduced. So these are all the little tricks that people use. You must be conscious of this. And that's the reason why I say all testing and certification should be done in the presence of those who know something about the subject, who can then detect such malpractices if any is attempted. I hope you found this presentation useful and wish you all the best in your environmental control initiatives.